today we are going to be talking about single source shortest paths. In the last class we looked at minimum spanning trees, Prim's algorithm for computing minimum spanning trees. This is a different problem and I will soon tell you what the problem is. What we will however find is that the algorithm is strikingly similar to Prim's algorithm. Okay. So, let us see what the problem is and what the algorithm for this problem is. So, once again we are given a graph and today we can assume that the graph is directed. So, this algorithm or this problem is well defined even for directed graphs. So, I am going to assume that the graph is directed. Okay. So, let us take a graph . Each edge has a length L is a function from the edges to positive reals, non-negative, we can have edges of length 0 also, right, and let us give edges length. So, let us say this edge has length 2, this has length 3, this is length 3.1, this is length 7, this is length 0.5, this is length 1.1, this is length 5. Okay. This could be a network of, let us say, the roads in a city. Okay. So, each length, so the length corresponds to the distance from this endpoint to this endpoint, and let us say these are one-way roads. Okay. So, I will at the end of this class I will tell you other applications of this problem, there are tons and tons of that. Okay. What is the problem? The problem is to find the shortest path. Let us say I want to go from this place S is also called the source. I want to go from S to T. T stands for termination, no, destination. Why should T stand for destination? You will figure out yourself. Yeah. Okay. So, I want to go from S to T, and clearly I would be interested in taking the shortest path. Right. How many different paths are there in this graph between S and T? 4 only. So, there is one path I go like this, then I go like this, and then I come back here. That is one path, right. The other path is I go like this, I come down, then I go like this, and then I come down. This is the second option. The third option is that I go like this, come down, I go straight. This is third option. Fourth option is that I go 2 and then 7, and then one other option is this, this and this. Is there one more? 0.55, 3. So, 3 I cannot come back, right, that is what I cannot come back on this. This is not a path, yeah, because this edge is directed in that manner. It would have been a path if this were an undirected graph, but not in this graph. So, actually this graph has only 5 different paths. So, it is a simple problem to compute the length of each path, yeah, and take the minimum. So, what is the length of this path? 8.6. Length of this? 7.7. What's the length of this?
8.6. No, no, sir.
2, 3, 5, 8.1. This is 9. This is 8.6. So if these were your GPAs, you would have preferred this. Yeah? But clearly we are interested in the shortest path. So we would like to take this path, 7.7, right? Because it's the shortest path, the shortest way to get to your destination. Yes? Okay. So can we always do this thing, as in list out all the paths in the graph, right? And just take whichever is the shortest, compute the length of each path and just compute the shortest? Huh? Not feasible. Why is it not feasible? Not practical. Why it's not practical? What is impractical about it?
It will take a lot of time. High time complexity.
High time complexity. Okay. Why high time complexity? Why should there be? Maybe a graph on n vertices never has more than n paths. Then it's a simple matter, right? Just list out all your n paths and just compute the length of
Cycle.
if it has a cycle.
It won't have
Right? Will you ever go along a cycle? You are looking for the shortest path, right? Why would you want to cycle? So, you know, you can ignore your, as in you would not, when you're listing out your paths, you will try and ignore cycles. Okay, so yeah, it is not feasible, but that is because the number of paths can be very large. What do I mean by very large? Let's look at an example. Yeah, very large means exponential here. So this is my graph. Edges are all directed left to right. Right, you get the idea. This is S and this is T. Right, okay, sorry, there are more such diamonds. This is T. Right, so right? So if there are n vertices, how many such diamonds are there? How many such diamonds are there if there are n vertices? Or let's do it the other way around. If there are k such diamonds, then there are how many vertices are there? K diamonds would count as 3k plus 1. Yes. Just do your counting correctly. Right? With each diamond I associate this vertex, and let's say the left end. I can't associate both, right? Because of that. So it will be something like 3k plus 1 vertices. How many paths are there between S and T?
2 to the power k minus 1.
2 to the k, yes. Why? Because for each diamond, I can either take the top part or the bottom part. So there are two options in each diamond. So I can have one path which just takes the top part always. One path that takes first का top, second का bottom, third का top, fourth का bottom, ऐसे ऐसे कुछ कुछ करके वो, right? So each diamond के लिए two options हैं, k diamonds हैं, तो 2 to the k different paths between S and T. Yes? Everyone follows this? अब k की वैल्यू कितनी है? अगर n vertices हैं हमारे, so k is roughly n by 3. So this is 2 to the n by 3 paths, roughly. Right? Now how large is this number? ये भी enumerate कर सकते हैं? नहीं. आपका लैपटॉप तो बहुत फास्ट है आजकल. नहीं. How large is this number? Two to the 30 is the number of particles in this universe. ठीक है? मतलब आपके पार्टिकल, आपके पड़ोसी के पार्टिकल, सबके पार्टिकल्स मिलाकर, that's the number of particles roughly. Of course, no one has counted it. This is an estimate. Okay, and 30 would be achieved for a graph of size 90, n equals 90 के लिए, which is not a, which is a very small number actually, right? These graphs are typically huge, you know, when you are trying to compute shortest paths and stuff like that. So it doesn't make any sense to do this kind of a, to follow such an approach to compute shortest paths. Okay. So what should we do? How can we solve this particular example? Can you think of a way of solving this example? Right. So of course there are lengths on all of these edges, which I have not written down, but you can imagine 0.5, 1, 1.1, 0.2, 0.3, 0.4, 0.8, 0. I've just taken some arbitrary numbers. What is it that you can do in this example to figure out the shortest path between S and T? Huh?
Compare the top and bottom path line.
Compare. So what you're saying is here, I am going to see, oh, 1.5 if I take this top thing, and 1.3 if I take this one, so I'll go bottom. And so I would have reached this point now. Yeah. And then from here I have an option of going 0.7 up or 1.3 down, so I will take this one, and now I would have reached this point. So what you are essentially saying is that to reach this destination, I will first have to get to this, then I will have to get to this, then I will have to get to this, and so on and on, right. So first I will have to go from here to here. So I can choose the, there are two options, and I can choose the better option of going from here to here. Yeah. And then I have to go from here to here, there is no other possibility in this graph. So I can choose the better option, and so on and on. Yeah. Now this works in this example, not true always, right. I have to get to this vertex, right, and I am starting from here. So but I do not know which is the first vertex I should get to from here, right. There is no such clear demarcation, as in saying that if I have to go from here to here, I have to clearly go from this vertex to this vertex. We can't say such a thing anymore. Yeah. So if I have to go from here to here, I can't say which is the first vertex I have to get to. Maybe I have to go through this vertex, maybe not. Can't say. Yes? Everyone with me? So that's part of the problem. So any ideas? How will we do this?
So we can again take a partition cell and keep S in the S in one partition and the others in the other partition, and then follow the edges in a
Keep it table.
No.
Keep a table of shortest path reached
The
till
shortest
now.
path from A to B must contain all shortest paths, as in whatever is a part of the path. If X is a part of the path from A to B, then A to X should also be a shortest path. So we can use some sort of a successively we can keep improving the path.
Okay. Okay, that's an important property of shortest paths, right? So this is one property we are going to be using. Right, so what he's saying is, suppose this is the shortest path from S to T. This is some path in the graph, right? There are some intermediate vertices I have not drawn. Let's say X is one of these vertices, right? Then the part of this path from S to X, that means this part of the path, what I am referring to is this part of the path, is the shortest path from S to X. This is also the shortest path from S to X. Why? This is, we are saying this is the shortest path from S to T, right? Why should it be also the shortest path from S to X? X is any arbitrary vertex. Right. So we are trying to arrive at a contradiction. We are saying suppose there were a better path between S and X, right? ये जो path है ये ज़्यादा घूम के तो जा रहा है पर ये छोटा है, right? So then the claim is that the shortest path between S and T is this blue path from S to X followed by this green path from X to T. Yeah? And there was nothing particular about X. Any vertex, for any vertex on this path, the shortest path from S to that vertex is this path. ठीक है, समझ में आ रहा है? बाय द वे ये ब्लू पाथ इसके बराबर लेंथ का हो सकता है पर इससे छोटा नहीं हो सकता. So this is also a shortest path from S to X. So that's all we are saying. This is also the की जगह a कर देते हैं. This part of the path is also a shortest path from S to X. ठीक है? So what does this suggest? This, this is giving you the following idea. अगर हमें S to T shortest path निकालना है, तो we will end up having to compute the shortest path from S to many other vertices, all the vertices on the path. Okay. So what the algorithm we are going to discuss today is actually going to compute the shortest path from S to every vertex in the graph. Okay. Not just T. So in fact what we are going to do is forget T. First step of the algorithm, forget T and just compute the shortest path from S to every vertex of the graph. Once you have computed the shortest path from S to every vertex of the graph, you also got the shortest path from S to T. ठीक है? So we will compute the shortest path from S to every vertex in G. ठीक है? So this problem is also called the single source shortest path problem. Right? Why? Because we are starting from one particular source and from that source we are computing the shortest path to every other vertex in the graph. Right? Sometimes this would be abbreviated as triple SP, single source shortest path. Okay. Now, given that we are not just interested in the shortest path from S to T, but the shortest path from S to every vertex in the graph, let's see what we can say about this example again. We are interested in the shortest path from S to every vertex in the graph. ठीक है? इस पिक्चर को देख के and without using your head too much, which vertex or the shortest path from S to which vertex is immediate? Adjacent ones? Minimum of the adjacent ones. We know by looking at this, we know that the shortest path from S to this vertex is 0.5. But the shortest path from S to this vertex is not 2. Right? So we can't say that I know the shortest path from S to every adjacent vertex. But we know for a fact that the shortest path from S, so if these are the adjacent edges or the 3 adjacent vertices, right? And suppose these lengths were L1, L2, L3, right? Let's assume L1 is less than L2 is less than L3, then I know for a fact that the shortest path from S to V1 is L1. Why? Why do I know this for a fact?
For reaching V1, you have to take one of the V2, V3, otherwise if you don't take
Huh? Yes, any other path, since it has to start from S, it has to take some edge out of S. If either it takes this edge or this edge or this edge. If it takes this edge, then the length of the path will be at least L2. Why? Because edge lengths are all positive. कोई नेगेटिव नहीं है इसके बाद. मतलब आप इसके बाद कुछ पाथ लेके यहां पर अगर पहुंचेंगे तो ये पूरे पाथ की लेंथ has to be at least L2, because this part of the length path is only non-negative. It cannot be negative, right? Similarly, अगर हम V3 से किसी तरह घूम घाम के V1 पहुंचते हैं तो the length of the path has to be at least L3. Yes? So what does that mean? The shortest path from S to V1 is L1. Okay? So just by looking at this, I can say that, so I am going to use D to denote distance, right? So distance of vertex V1 I know is L1. What can I say about the distance of vertex V2? D of V2, what can I say about that? Greater than L1? Greater than L1? Greater than L1, okay. And less than or equal to L2. Let's just put that down. Okay. And similarly, distance of V3 is less than or equal to L3. ठीक है? तो शुरू में हमें, अगर हमारा ये सोर्स वर्टेक्स है, ये इसके एडजेसेंट वर्टिसेस हैं, तो इनमें से एक एडजेसेंट वर्टेक्स का डिस्टेंस एग्जैक्टली पता चल गया और बाकी वर्टिसेस का डिस्टेंस हमें पता नहीं चला अभी क्या है. वी डोंट नो द करेक्ट डिस्टेंस, but we have an upper bound on the actual distance. Yes, this is an upper bound, right? That the actual distance is only less than this value, right? Okay. So what are we going to do now? So we know the actual distance of V1. Now how can we extend it? How can we find out the I have to find out the distance from S to every vertex.
Assign all of them initially the direct lengths that we have, and at each vertex we have what is the shortest path here, length of the shortest path we have found till now. And then any point, if we at vertex we found with a visited vertex, then compare to the length which is already stored in that vertex to the sum of the path, sum of the vertex we just found.
चलिए देखते हैं. अच्छा, सो ये हमारा S है. V1 का हमें डिस्टेंस पता चल गया, करेक्ट डिस्टेंस. अब हमें किसी तरह किसी और वर्टेक्स का डिस्टेंस निकालना है, करेक्ट डिस्टेंस निकालना है. V1 से मान लीजिए एक एज ऐसे जा रही है, एक एज हमारे V2 को जाती है और एक एज V1 से V3 को भी जा रही है. ठीक है, और V1 से एक एज और ऐसे जाती है. आई एम जस्ट टेकिंग एन एग्जांपल एंड सून वी विल concretize the algorithm, right? So don't worry too much about it. Let's say V1, V2, V3, ये V4 है और ये V5 है. L1, L2, L3 edge lengths the. Let me now replace them by numbers because otherwise we will keep having lots of L's, right. So, let me put down numbers 0.7 and let us say this is 1.1, this is 2.3, right. So, L1 is the smallest. Okay. Let us put down more numbers. Okay. Let us try and understand what I have done here. Just to separate this out. So, we know this, let me circle it. We know the correct distance of vertex V1 and the correct distance of vertex V1 is 0.7. Okay. Now, looking at this picture, can I say, so this is the only, there might be other edges and so on and on between these vertices. I have not shown those edges. I have just looked at the edges going out of V1 now, right, and there are 4 edges going out of V1. Now, looking at these edges, can I say for certain what the shortest path to some other vertexes? I am not saying to this specific vertex, what is the shortest path? I just want to know the correct shortest path to some one vertex.
Take all the outgoing edges and mark and store the distance from there, from that side. And then from that edge again to all outgoing edges till we find the end. And then in the queue keep on taking the edges and keep on storing. Take the minimum if we get a minimum.
No, you are going into details, right? Let's understand what the idea is. Okay. Let's look at vertex V2 or let's start by looking at vertex V3. ठीक है, अभी तक we had seen only this edge and we said that the distance of V3 from S is less than 2.3. That is what we had said so far, it is less than 2.3. Now, can I say something better?
Because when we visit V3 from this,
Because now I see this edge from V1 to V3.
you can update.
I know the shortest path from S to V1. What is it? 0.7. I see that the length of this edge is 0.3. So, 0.7 plus 0.3 means 1. So, I have found another path, yeah, from S to V3 of length 1. Yeah. Yes. So, I can say that the distance of V3 from S is less than or equal to 1. Yeah. Okay. Now, let us look at vertex V2. Pardon? Yeah, we will come to why it is exactly 1. One step at a time. Yeah. So, all I will say is that okay, V3 has the distance of V3 from S is less than or equal to 1. That is all I can say at this point, right, till I bring in some additional argument. So, distance of V3 from S is less than or equal to 1, that is all I can say. What can I say about the distance of V2 from S? Well, I have found another path to V2, that is the path which goes from S to V1 and then follows the edge V1, V2. But this path, any such path is going to have a length of at least 1.2. In particular, there is only one path at this point, right, but this has a length of 1.2. And since earlier I had a length of 1.1, well, I have not found a better path to V2. What can I say about V4 now? Well, V4, abhi tak there was no path from S to V4. Now I am seeing a path from S to V4 whose length is, well, this is an edge from V1 to V4. So first I get to V1, right? I know the shortest path from S to V1, that is of length 0.7. So this is 1.1, and distance to V5 is 1.3, 0.7 plus 0.6. Right. So these are my new upper bounds on the distances. I call them tentative distances. Right. This of course is fixed, final. This will not change. This was the shortest distance. This can never reduce. But the other distances might reduce as the algorithm proceeds. For instance, this distance, this tentative distance, which was earlier 2.3, has now reduced to 1.1. Sorry. This did not reduce. This earlier was not reachable at all. Let's say it was infinite earlier. Now it's become 1.1. Right? And this also came down from infinite to 1.3. Now, what I'm claiming is that let me look at the smallest of these, which is 1. And this is the correct distance of V3 from S. हाँ समझ में आया ये मैं क्या कह दिया? At least 3 edges? No, we can't say such a thing.
But in this particular case, I
Okay, धीरे धीरे करते हैं इसको. हाँ ठीक है. So this is what, so let's first say what the algorithm is, and we'll have to prove its correctness, and we'll have to look at its implementation, right? And we have 3 lectures to do it. So let's not rush ourselves. This is not a straightforward algorithm, but let's understand what the algorithm is first, right? So once the algorithm is ingrained, then we will see why it is correct. So what's my algorithm now? So my algorithm is going to have a set S of vertices, and S होगा तो बाकी का क्या होगा? S complement होगा. ठीक है? What does this set denote? This set is the set of vertices to which I have found the shortest path from little s. ठीक है? So what is going to happen in this algorithm is, with every step of the algorithm, I would have found the shortest path to one more vertex. When I say I have found the shortest path, I mean the shortest path, right? Not an upper bound or any such thing. I have found the correct value of the shortest path from S to that vertex. So हर step पे I would include one vertex into the set. At every step, I will include one vertex into this. So at any point, this is the set of vertices which I have found the shortest path to, and this is the set of vertices for which I have not yet found the shortest path. I just have an upper bound on the value of the shortest path. I know that the shortest path is less than this number, but I don't really know what the correct value of the shortest path is. So each of these vertices has an upper bound on it. So if this is a vertex V, let d of V, so let me write down, for all V in S complement, d of V is an upper bound on the length of the shortest path from S to V. You understand what I mean by upper bound, right? It is a quantity which is only larger than the length of the shortest path. It can never be smaller than the length of the shortest path. And for all V in S, d of V is the length of the shortest path. Okay? I am just telling you what are the various invariants the algorithm is going to have. Okay? These quantities would be upper bounds and this would be the actual values. Now I will tell you how do I figure out, how do I move one vertex from here to there, which is the vertex I move from here to there, right, and what happens when I move that vertex. So first, which is the vertex I move from here to here, right, yeah. So I find the vertex in S complement for which D is minimum is moved to S. Okay? So I have my S complement, I have my S, I have these tentative distance on all of these vertices. जिस vertex का ये सबसे छोटा होगा, I will move that vertex here. ठीक है, तो मान लीजिए ये 7 था, ये 3 था, ये 2 था, ये 11 था, ये 9 था, ये 1.1 था और ये 8 था. So this is the vertex which will move from S complement to S. ठीक है, so you understand what moves from S complement to S. Now what happens when this move is done? How do these numbers change?
2 plus length of the edges.
Right. So how do we update? That's what we have to determine now.
Add the value of the length of the
But the vertex we are moving.
and edges
Add it to the
and then check it.
सबको समझ में आ रहा है हाँ? ओके सो मान लीजिए ये वर्टेक्स W है जो हम मूव कर रहे हैं. ये S कॉम्प्लीमेंट है, S कॉम्प्लीमेंट माइनस W और ये S है. ठीक है, मान लीजिए एक एज यहां से इस वर्टेक्स पर जा रही है. ये वर्टेक्स, लेट्स से आई एम लुकिंग एट दिस एज. इस वर्टेक्स के ऊपर डिस्टेंस लेवल अभी d की वैल्यू 9 है. इस एज की लेंथ मान लीजिए 3 है. ठीक है, और ये W का हमने शॉर्टेस्ट पाथ क्या निकाला है? देखिए जब हमने इसको यहां मूव कर दिया तो ये 1.1 ही रहा. फ्रॉम व्हाट वी हैव सेड, the right distance from little s to this vertex W will now become 1.1, will be 1.1. So I know that from S I can reach W using a path of length 1.1. So which means that I can reach this vertex by using a path of length 1.1 to here and 4.1. So I can change this 9 to 4.1 now, and this is my new upper bound on the length of the shortest path from S to this vertex. Yeah. So this is how I am going to update these labels. These Ds are also called distance labels. Okay? I have not told you, you have a slight inkling of why we are doing what we are doing, right? But we have not discussed why it is correct. We will do the correctness for this. So don't lose heart, right? I first want to make sure you understand what the algorithm is. Okay? Okay. So understanding will be complete after we write down the pseudocode. Yeah. So let's do that. So this is going to be almost exactly like Prim's algorithm with a very small modification, right? So you can now start telling me what I should do. What should I do? What should my initial values of distance labels be? Infinite, right? Distance label, recall we said, is an upper bound on the length of the shortest path from S to that vertex. Since initially I have no clue what those things are, I put every vertex, I give every vertex a distance label of d of v equals infinite and d of s is 0. Distance of s is 0 because it's right. Now what should I do? Right, I should take the vertex with the at any step. What do? I take the vertex with the smallest distance label. So all of these guys should be put into a heap. Yes. So for all v belonging to v, dv equals infinity and h dot insert v comma dv. Yeah, I've inserted the node v with priority dv, and this guy also I'm going to insert h dot insert s comma 0. Right. So the minimum. What? Oh, acha, we have already inserted. You are saying there. Let's say decrease. Okay, let's call it decrease priority. Okay. Right. Now in my heap, the minimum, the top element will be S. I should now remove this element. What should I do? I should remove the minimum. Right? Did I also remove the minimum in the case of Prim's algorithm yesterday? Or we just did a find min, right? That was a mistake. Please correct that in your notes. Right? We don't just have to do a find min, we also have to remove it from there, right? Because recall, the only vertices that we are keeping in the heap are the vertices on the S complement side. Okay, so let's look at this and you can then go back and look at your Prim's notes again. So what should I do first? I should remove the minimum element. So h dot delete min, and let's say this is vertex v. So I get the minimum element, the vertex with the minimum priority, and let's say that's vertex v. What should I do now? So this I got as the minimum vertex. I should look at the edges.
Adjacent to this, to update the priorities.
Right? I should look at the edges going out of this vertex. Or the same as saying, let me look at the adjacent vertices. So for all w, let me just say out adjacent so it's completely clear what I'm saying. out adjacent to V, do. So I am looking at this vertex W which is out adjacent to V. Now I have to update its label. When should I update the label of W? W already has a label, right? And what is that label? That label is an upper bound on the shortest path, right? Basically that label is saying कि अभी तक मुझे इतने लेंथ का पाथ मिला है W तक का, अभी तक इतने लेंथ का पाथ मैंने देखा है, ठीक है। कब हम उसकी वैल्यू रिड्यूस कर सकते हैं? जब अब हम नाउ वी आर सीइंग अ शॉर्टर पाथ। हाँ, right. No, but what she is saying is that we should update W only if it is in S bar.
बट वो दूसरा बात आएगा बड़ा ही आएगा.
Yeah. So, देखिए, even if I were to not worry about that, the point is, I have said that I have already found the shortest path to W. If W were in S, and that means I have already found the shortest path to W, then there is no way it's getting updated now. Because if it's getting updated, there is something seriously wrong with what I am saying. Yeah? Think about this. We don't really need to maintain this information in this particular case. Okay? So, when should I update W or distance label of W? So, if I find a better path to W, and what would be the better path? Through V. So, D of W equals minimum D of W, comma D of V plus L of V W. Yes? This is the other path I am seeing to W. And if this is shorter, then let us put this as the new label. Everyone understands ये मैंने यहाँ delete में क्यों किया? Because S complement में अब वो vertex नहीं रहेगा, वो vertex move कर गया है S complement to S, right? And the only vertices in the heap are the vertices in S complement. उन्हीं के तो हमें distance, उन्हीं का हमें अभी shortest path निकालना है। और कुछ करना बाकी रहता है? हाँ? तो वो तो यहाँ हो रहा है। ओ सॉरी, सो ये हमने DW चेंज करा, तो अब हमें इसकी अपडेट करना पड़ेगा। सो H डॉट डिक्रीज प्रायोरिटी W comma this is together. ठीक है, मतलब this statement would not be executed, मतलब you can do it more carefully, this implementation, only if DW decreases should you call this. But waste of time. You will have to follow a few pointers to get to the heap, make a comparison, all of that, right? ठीक है? So we are done. At the end, where are the shortest paths? Sorry, what have we found out? We have only found out the length of the shortest paths, and they are all sitting in D.
So when you are updating this DW,
Yeah.
you can maintain a parent array also, and you can update PW to V.
Which is the
Okay,
point?
we come to that. We come to that in a minute. ठीक है, तो एल्गोरिथम सबके समझ में आ जाना चाहिए अब तक कि क्या हो रहा है। कुछ हो नहीं रहा है, इट्स नॉट वेरी डिफरेंट फ्रॉम प्रिम्स। प्रिम्स से कहाँ डिफर कर रहा है ये एल्गोरिथम? बताइए मुझे. We don't have to maintain S. And basically यहाँ इस step में, right? This is similar to the version of prims, the second version of prims that I talked about, where हर एक vertex के ऊपर हमने एक label रखा हुआ था, ना कि edges वाला. तो हमारे heap में, you recall the second version of prims? What was that? We had maintained S complement, and for every vertex in S complement I had one label. And what was that label saying? Look at all the edges going from this vertex to S. The minimum of these edges would be the label here. Yeah? Now the label is saying something completely different in the case of Dijkstra's algorithm. This was Prim's algorithm, right? This label V equals minimum of, अगर ये लेंथ हमारी L1, L2, L3 हैं, तो L1, L2, L3, minimum of these three है ये. Now, again we have a similar thing. We have each of these vertices has a label. We are calling that label D now. Yeah, but D is not the minimum of these three. It's not that. Yeah, D is not the minimum of L1, L2, L3. ठीक है? D has some other semantic which we will see later. ठीक है? Can someone hazard a guess here? What do you think is D? Minimum of? Huh? Good. Min of, yes. The value of dV is min of dW1 plus L1, comma dW2 plus L2, comma dW3 plus L3. ये जरूरी नहीं है मेरे सारे एग्जाम्पल में तीन ही एजेस जा रही होती हैं, बट ऐसा जरूरी नहीं है. ठीक है? ओके, बाकी सब कुछ काफी हद तक सिमिलर है. आप ये सारे वर्टिसेस को एक हीप में रखते हैं. ठीक है? ऑल दीज वर्टिसेस आर पार्ट ऑफ अ हीप. प्रायोरिटी इज दिस लेबल here and the priority is this D value here. हर स्टेप पे आप मिनिमम लेते हैं. ठीक है? और मिनिमम लेके आप अपडेट करते हैं, और अपडेट इस तरह करते हैं कि ये सिमेंटिक बनी रहे यहां पे और ये सिमेंटिक बनी रहे यहां पर. इस तरह हमें अपडेट करना है. ठीक है? we'll see why this is true. This we'll see when we are doing the correctness of the procedure. Yeah? So who can tell me what the running time is? V square log V. Why V square? Oh, yeah, I understand, but why n square log n? Huh? It's again summation degree log n. सेम ही तो है. अभी तो मैं कह रहा हूँ सेम है, सेम है, सेम है, फिर आप रनिंग टाइम कुछ और ला के बता रहे हैं. ठीक है? ये आपको ये काउंट करना है कि हम यहां पर वी आर स्पेंडिंग टाइम प्रोपोर्शनल टू द आउट डिग्री ऑफ दिस वर्टेक्स, or the number of times we are calling this loop. Time will be log n times that because of this decreased priority operation, right? Because each decreased priority operation takes time at most order log n. राइट एंड एक ये ऑपरेशन हम कर रहे हैं हर बार. ये ऑपरेशन कितनी बार हो रहा है टोटल? n या n minus 1 times, right? Because this operation corresponds to removing the vertex from S complement. तो आपके शुरू में n vertices थी S complement में n minus 1. हर बार आपने एक एक रिमूव किया तो n minus 1 times आप इस ऑपरेशन को करेंगे. Each time it takes log n time, so it will be n minus 1 times log n. Right? This is now I realize this is the mistake I made in the Prim's algorithm. वहाँ पे भी हमें delete करना होगा because the semantic is the same. It's the vertices in S complement are the ones in the heap, and so when I'm moving a vertex from S complement to S, I have to remove it from the heap. Right? So you have to do a delete min operation. We just said find min. Yeah, if you don't do it, will be an infinite loop because the same thing will keep coming as the min. ठीक है? तो वो find min को आप अपने काट के delete min कर लीजिएगा अपने notes में. Great. So this total running time, let me put it down. No, not n but m. Not n but m. Why? Because we are the total time, the total number of times this operation is being executed is order n. ठीक है? Yeah. So with that we will end today's discussion on shortest paths, but we'll continue this because we have to prove the correctness of this algorithm. We also have to see how to find the shortest path, because here we have only computed the length of the shortest path from S to the root.